We started with the inverse functions in general. We're probably more interested in the inverse trig functions, which is going to allow us to do some interesting problems. So let's find them. So the inverse sine of x. Well, let's have a look at y equals sine x. And here it is, good old sine x. We know it's got an amplitude of 1. And we'll just draw it in and I'll go crazy. I'll go from minus 2 pi to 2 pi. So domain's all real x. Range is minus 1 to 1. But obviously it fails the horizontal line test. No good. So we just want a piece of the curve. There's so many different pieces we could pick. But as I mentioned to you before, we would like to get positive. 0 is usually a good thing to grab as well. So the logical piece, and by the way, if you haven't worked it out yet when you did the first example, you're basically looking for a piece that is continually increasing or continually decreasing. Because as soon as it turns, it's not going to have an inverse. So I reckon from minus pi on 2 to pi on 2 would be a logical spot to pick. And we'll get our complete range when we do that. So we swap the x and the y's and we make y the subject. Well, basically we've created this new function called the inverse sine function. So there it is, y equals inverse sine x, which is on your calculator. There's your domain. Hang on, wait till I write the range up. So the domain and the range swap. This explains why when you go to your calculator, it only gives you answers from minus 90 to plus 90. Because your calculator is dealing with a function. It can only give you one answer. It can't give you multiple answers. So let's draw it. Now, the scale of my graph there, it's a bit hard to do it on the same diagram. So obviously you can see how large 1 is compared to pi on the x-axis, which is 3 point, whatever. So I'll just draw it underneath here. Here we go. Whee! All right. So it is a sine curve. It's not a tan curve. So don't draw it like a tan curve, but you're actually drawing a sine curve. It is winding along the y-axis, but we've just got a piece of it. Okay, let's do cosine. Draw in the basic one. Now I've got to get a different piece this time, because if I go from minus pi on 2 to pi on 2, not going to work. Many different ones we could pick, but this time, because I want to get positives, go with 0, it would make sense to go from 0 to pi. No, fails horizontal line test. We'll restrict 0 to pi. It'll get all the range. So the range and the domain will swap over. And this is explaining why when you go to your calculator, when you're dealing with cosine, it will give you obtuse angles as an answer. Because its range is from 0 to pi. And let's draw that one. Again, I can't really use the same diagram, so we'll draw a new one underneath. There we go. Now be real careful when you draw these, by the way. It's so easy to flip that the other way around because you're so used to seeing pi and 1 and things like that. But okay, complete the set. Tan. This one was a little bit different, of course. It has no amplitude. We have a series of asymptotes. There we go. Again, fails the horizontal line test. We really just need to pick one of those branches. The logical branch is to pick the one that goes through the origin. And we get inverse tan x. Once again, domain and range swap over. Again, explaining why when you go to calculator, inverse tan, it also gives you answers from negative acute angles to positive acute angles. Okay. Let's draw it up. This one's a bit easier because the x and y swap, so we now have horizontal asymptotes, and there's our tan curve on its side, if you like. Right, some rules. Inverse sine of negative x is equal to the negative inverse sine of x. If you look at the graph, it's an odd function. So it must satisfy the function negative x equals negative function x. Inverse cos is interesting. It's pi minus the inverse cos of x. That's to do with, it's an odd function that's been shifted up pi on 2. If you look at your inverse cos graph, if you were to rotate instead of around the origin, but if you were to rotate around pi on 2, it has 180 degree symmetry. So it's shifted up pi on 2. That's why we add the pi in. And inverse tan is also an odd function. So inverse tan of minus x is minus inverse tan of x. Basically, all three are sort of odd functions. I mean, inverse cos is not, but it's been shifted up a bit. Inverse sine of x plus the inverse cos of x will always be pi on 2. In fact, there was a question in last year's HSC where you actually had to prove that. That was the 3-up paper, yes. Basically, angle sum of a triangle. All right, let's see what sort of questions we might get. Find the exact value of inverse tan root 3 minus inverse tan of 1. So because we're dealing with inverse functions here, there is only one answer. It has to come out of the range of the function. Well, these are both going to be acute angles because they're both positive. So we'll have pi on 3 minus pi on 4, pi on 12. So when they're positive, not much to think about really. We know it's going to be an acute angle. It's when they're negative we have to think. Because when they're negative acute angles, except inverse cos, it's going to be an obtuse angle because of the range of the function. So in this case, inverse sine of minus a half will give me negative the acute angle. Alternatively, we could convert it using our rule up the top there and say, well, inverse sine of negative a half would be the same as minus the inverse sine of half, so it'll become plus. I just made it the negative acute angle, so we get minus pi on 6, and we get 5 pi on 12. The cos of the inverse sine of 40 on 41. What you have to think of is inverse sine, inverse cos, inverse tan, it's an angle you're talking about. So when we say the cosine of inverse sine of 40, we're saying, what is the cosine of an angle? I think the easiest way is to draw a triangle. So I say, well, look, okay, I'll make it one of the angles. There's the angle. I'll call that angle there the inverse sine of 40 on 41, which means opposite over hypotenuse is 40 on 41. Bit of Pythagoras gets me to the other side. The question then is now saying, what's the cosine of that angle? Ah, it's 9 on 41. Inverse sine of the sine of 5 pi and 6. This is where we have to be real careful, because it is so tempting to say the answer is 5 pi and 6. Because you go, oh, inverse sine and sine, surely they just cancel. Like we saw with inverse functions, they cancel. We're left with just a number. Problem is, inverse sine gives me answers that are either negative acute or positive acute. It can't give me 5 pi on 6. So the equivalent answer for 5 pi on 6 would be pi on 6. Right? Has to be either acute or negative acute. Well, we know the sine of 5 pi on 6 is a positive number. Therefore, I'm getting a positive acute angle here. The sine of 2 inverse cos 3/5. Right? Inverse cos 3/5, we're just talking about an angle. It's really saying sine of 2 theta. So I know, and I can make life even easier for myself by saying, oh, I'll let theta equal that angle. So I'm not confused with the inverse cos bit, I've just got a theta there. And so I'll draw a diagram up again, if that's theta. Well, inverse cos is 3/5, so adjacent over hypotenuse. Bit of Pythagoras, I've got the other side. Now sine 2 theta, well that's 2 sine theta cos theta. Now I'll just read off my triangle. So I get 2 times 4/5 times 3/5, 24 and 25. The inverse cos of 2 cos pi on 3. Well, I don't have a double angle result for inverse trig, because remember that's not a double angle now, it's a double ratio. But guess what? I know what cos of pi on 3 is, so I can just work it out. 2 times a half is 1. It's just asking me, oh, what's the inverse cos of 1? Which is 0. Tan of the inverse sine of 2/3 plus the inverse cos of a quarter. Remember, inverse trig are angles. So, all right, I'll let alpha be the inverse sine of 2/3. Let me draw up a triangle. Opposite, hypotenuse, bit of Pythagoras. Good. Beta will be the other one. Draw the triangle. Adjacent, hypotenuse, bit of Pythagoras. So we're now saying tan of alpha plus beta, which of course we know is tan plus tan on 1 minus tan tan. And we substitute in. And, well, a bit of playing around to do. But eventually we get there. 2 plus 5 root 3 on root 5 minus 2 root 15. So 1b, playing around with these new functions we call the inverse trig functions.